And maybe you have to press. Yes.
Hello, good afternoon. My name is Ozgur. I'm a PhD student at Pennsylvania State University. Today I will discuss our research, which is the geological carbon storage resources in Pennsylvania and the regions. So I have been doing this research partially funded by the PetroChina and also with the supervisions of Chiao and Dr. John Wang. So now let's check the outline of the presentation. I will first introduce the concept of carbon capture and storage. Then I will discuss the classification of geological CO2 storage resources. After that, I will move on to the analysis of the previous assessments of geological CO2 storage resources in the study area. Then I will discuss our assessments of the CO2 storage resources in Marcellus and Oriskany formations in the Appalachian Basin. And finally, I will conclude the presentation with our key findings and their implications. So governments and industries worldwide have been working on developing carbon storage projects to address the carbon capture and storage. And this figure here shows the procedure of the geological CO2 storage, which starts with capturing and separation of carbon from its large point sources, such as power plants, and then storing it into the underground geological formations by injection. And this is before the carbon is released into the atmosphere. And the procedure of geological storage starts with regional geological investigations. So there are 5 main potential CO2 storage formations as previously defined by US Department of Energy. These are saline formations, depleted oil and gas reservoirs, unminable coal beds, organic rich-shales, and basalt formations. And the geological CO2 storage will be safe and permanent when the depth of the storage formation exceeds the 2600 feet to provide enough pressure for carbon to be stored in supercritical phase. The next point is that the storage formation needs to be sealed by an impermeable caprock with sufficient thickness to prevent possible leakages. And the other point is that the storage formation needs to have sufficient porosity, permeability, and thickness for carbon storage. And also, the salinity of the formation water in storage formation should be higher than 10,000 parts per million to protect the potable groundwater. Potable groundwater should be safe as well. So now let's briefly discuss the CO2 trapping mechanisms. There are 3 main categories of the mechanisms. The CO2 can be trapped in subsurface geological formations by stratigraphic, structural, and residual trapping. And the CO2 also can be trapped by solubility, mineralization, and adsorption trapping, which is involved in chemical trapping class. And the CO2 can also be hydrodynamically trapped with a combination of physical and chemical trapping. Here in these figures, we see the operating time frame and storage security of the mechanisms. When we see the residual trapping, dissolution trapping, and mineralization, we see that these mechanisms require higher injection periods, which makes them like these mechanisms contribute less than the other trapping mechanisms. However, these mechanisms provide a more secure and safe trapping mechanisms for geological CO2 storage. So now let's briefly discuss the geology of Pennsylvania, which is the main point of the study area. The figure at the left shows the geological map of Pennsylvania, and the reviewed region includes Appalachian and Michigan basins in the northeastern and northern United States. And the Appalachian Basin is defined as the foreland retroarch sedimentary basin extending from New York to Alabama in the northeastern United States. And Pennsylvania is located in the north-central portion of the basin. And it is comprised of 6 different physiographic provinces. The Michigan Basin, on the other hand, is an intraprotonic basin that extends from Michigan to Wisconsin. And also, the stratigraphic column of Pennsylvania here shows that the Granville complex, which is the metamorphic rocks in Proterozoic age, constitutes the basement rocks, and the stratigraphy of Pennsylvania generally consists of the Paleozoic formations. The thickness of the formations increases from northwest to southeast Pennsylvania, and the main storage targets for carbon includes Cambrian basal sandstones, Ordovician Utica shale, Lower Silurian Medina Tuscarora formation, Lower Devonian Oriskany sandstone, Middle Devonian Marcellus shale, Upper Devonian sandstone reservoirs, and late Carboniferous coal formations. So the geological CO2 storage resources in this study is classified on the basis of Society of Petroleum Engineers classification scheme, and this figure represents an overview of the previous classification systems in the literature, and SPE classification scheme is highlighted by yellow, and the total CO2 storage resources represent the storage resources in both undiscovered and discovered geological formations, which represents the total pore volume, and the prospective storage resources represents the undiscovered geological formations, which requires less major projects. The discovered storage resources is classified into contingent resources, storage capacity, and stored. The contingent resources are the resources related to the projects that are not commercially mature enough. The storage capacity is the resources with commercially that the CO2 can be injected commercially, and the term stored represents the amount of CO2 injection. So now let's briefly discuss the previous assessments of the storage resources. So in this overview, we included the Midwest Regional Carbon Sequestration Partnership, US Department of Energy, and US Geological Survey studies. So the MRCSP assessed the geological CO2 storage resources in 3 different phases, phase 1, phase 2, and phase 3. And for Pennsylvania specifically, they assessed the resources in collaboration with Pennsylvania Geological Survey. For the other states as well, they collaborated with the other states' geological surveys. And in phase 1 research, they assessed the total pore volume of the storage formations in Pennsylvania. And in phase 2 research, they conducted 3 small-scale injection tests, which is marked by yellow stars in Michigan, Kentucky, and Ohio. And the highest CO2 injection occurred in Michigan with 60,000 metric tons of CO2 into the basalt dolomites in northern Michigan basin. And in phase 3 research, they extended the scale of the research and conducted a large-scale injection test in the northern Michigan basin, and they succeeded 2 million metric tons of CO2 injection. So the US Department of Energy, on the other hand, they assessed the contingent CO2 storage resources, or in other words, technically accessible CO2 storage resources, by incorporating storage efficiency factors into their volumetric calculations. So the difference between contingent and total CO2 storage resources is that in contingent resources, they assessed the fraction of total pore volume that the CO2 can be successfully injected, because you cannot fully inject the CO2 in all total pore volume, which might be related to geological or geophysical cutoffs. And these equations represent the estimation of the contingent CO2 storage resources into different storage formations, including oil and gas reservoirs, saline formations, coal formations, and organic rich shales. And the important parameter here is the storage efficiency factors, which can be calculated by Monte Carlo sample. So US Geological Survey, like the purpose is similar to the US Department of Energy, which is the, again, estimation of the contingent CO2 storage resources. However, the difference in this study is that they defined a storage assessment unit, which illustrates the storage formations and seal rocks. The storage formations is subdivided into depleted oil and gas reservoirs and saline formations in this storage assessment unit. And here is the volumetric equation that the USGS followed to assess the CO2 storage resources. It is subdivided into buoyant trapping and residual trapping storage resources. Buoyant trapping is for the depleted oil and gas reservoirs, and residual trapping is to estimate the resources in saline formations. Residual trapping occurs when the carbon is injected into the storage formation. However, when the capillary forces exceeds the buoyant forces, we see that the CO2 can residually trapped. The buoyant trapping is similar to the stratigraphic and structural trapping. And these resources are estimated based on the pore volume and storage efficiency. The buoyant trapping pore volume is estimated by summing the initial hydrocarbons in place and the US Geological Survey's national buoyant gas assessment outputs. And the storage efficiency of buoyant trapping is a function of mobility of CO2, irreducible water saturation, and sweep efficiency, which is defined as the storage efficiency factors for area and thickness. The residual trapping pore volume is represented by these parentheses, which is equal to the pore volume of storage formation minus pore volume of buoyant trapping pore volume. Buoyant trapping pore volume, which was previously calculated, and the storage efficiency of residual trapping is related to post-inhibition capillary trapping model of US Geological Survey. So based on this review, we assessed the Marcellus Shale and Ozgur sandstone in terms of their CO2 storage potential. And we analyzed different geological maps, including structural contour, isopac and porosity maps of these formations and other input parameters. And we developed the regional geological models to calculate total and contingent CO2 storage resources in these formations. And so these volumetric equations at the left and right represents the CO2 storage in Marcellus Shale and Ozgur sandstone. For Marcellus Shale, we have the free CO2 storage and adsorbed CO2 storage, and the geological parameters and storage efficiency factors represent these mechanisms. And for Ozgur sandstone, Ozgur sandstone is regarded as a storage formation with solubility trapping mechanism, and it includes the storage volume, porosity, free CO2 density, and storage efficiency of saline formations. So now let's discuss the results for Marcellus Shale. As also seen in these distribution figures for CO2 storage, the total and contingent CO2 storage resources was estimated as 129 gigaton and 15 gigaton in the Appalachian Basin, and Pennsylvania approximately constitutes 64% of the study area. And these distribution maps shows that the red areas in the northeastern Pennsylvania includes the highest CO2 storage potential. And for the Ozgur sandstone, the total and contingent CO2 storage resources were estimated to be 44 gigaton and 0.9 gigaton. And the distribution maps shows that the West Virginia has relatively higher CO2 storage potential when compared to Pennsylvania. And in Pennsylvania, the counties in the southern portion of the state, such as Fulton and Somerset, has the greatest CO2 storage potential in the Ozgur sandstone. And now let's discuss briefly how this study contributes to the previous knowledge on the geological CO2 storage resources in the study area. And the MRCSP previously assessed the CO2 storage in these geological formations. We updated the Oriskany sandstone, the CO2 storage resources, and we also added the resources in the Marcellus shale because the MRCSP didn't conduct any study in organic rich shales. And the US Department of Energy also, even though they developed a methodology for shales, they didn't publish the results because of higher degree of uncertainties. And this study was the first one to publish the results for the organic rich shales, including Marcellus shale. And the total CO2 storage resources is, following this assessment, 781 gigaton in Pennsylvania, and the contingent CO2 storage resources is estimated to range from 28 to 30 gigaton in Pennsylvania. So to conclude the presentation, we conducted a critical review of the previous geological CO2 storage assessments in the study area, and the total CO2 storage resources in Pennsylvania is 781 gigaton, and the contingent resources is estimated to range from 28 to 30 gigaton. And the northeastern and southern Pennsylvania provides highest CO2 storage potential in Marcellus shale and Oriskany sandstone. Thank you very much. These are the references. I'm happy to get your questions.
Can you comment on the cost?
Comment what?
On the cost for CO2 storage at these different locations.
Cost of CO2 storage. So the only MRCSP applied some injections of CO2. So it is still in the phase that determining the possible storage formation underground to drill into which cost. Actually, in the study I didn't check the cost of the study, but I can.
Can you give an order of magnitude?
Order of magnitude about cost?
Yeah. How much dollar per
So
ton?
it should be like for an injection well, it should cost like $6 to $7 million.
And
yes,
you can
in the range of $1 million. Like for an injection well, because it depends on the depth of the formation. So Marcellus shale, like it is like 7,000 feet. Marcellus shale depth 6,000 to 7,000. So drilling an injection well and also additional well operations would at least require a couple of $1 million, like $5, $6, $7 million. Yeah.
Thank you very much.